Just as a reminder, remember relation from A to B is just a set of ordered pairs, okay? Inside the Cartesian product A cross B, it's a subset of A cross B. Then we talked about relation on a set, which is when A and B are the same set. So as a relation on A, this just relates, it's a subset of A cross A, a set of ordered pairs, and the way to think about it is that you are saying how the elements inside the set are related to each other, whatever specification you decide to do, okay? All right, and then we talked about some properties we discussed reflexive. Remember, reflexive means every element has to be related to itself. Then we talked about symmetry, and definition. A relation is symmetric if every time that A is related to B, then B has to be related to A. Okay, so when you flip it, they are also related. So let me actually write down all the properties that we are interested in, and then we do a couple more examples. So let A be a set, and R a relation on A. Okay. So remember, what this means is that R is a subset of A cross A. Okay, that's what it means. All right, so then number one, I'm just going to write all the definitions so we have them all in one place. So we say that R is reflexive. So R is reflexive if for all A in A is related to A. Okay? So A is related to A. And then let me write the inverse here. So i.e. so all elements, what I would say, all the pairs A comma A are in R. Okay, so it has to have all pairs of the form A comma A. The other notion that we talked about was symmetry. So R is symmetric if for all A in A, for all B in A, we have that A related to B implies that B is related to A. So in common words, what we're saying here is that if the other pair A comma B is in the relation, then when you flip it, it has to be there. So i.e. if AB is in the relation, then BA must be in the relation as well. Okay? And we kind of talked about these two last time, so I'm just going to write the other conditions. So let me say what it means to be antisymmetric, transitive, and also there is a notion of irreflexive. Okay, you are going to see that in the homework and in the videos and so on. So irreflexive is not really the opposite of reflexive, but in a sense, reflexive requires every single other pair to be of the form A comma A to be in the relation. Irreflexive means that no element is related to itself. Okay, so there cannot be an A comma A in the relation. Let me actually write that down, get it out of the way. So number 3, R is irreflexive. Okay, it's 1R or 2R? I think 1R. It should be 1R. But now I'm not sure. It looks weird.
I think it's 2 R's.
And now I'm not sure if I should write an E here or an I. And I don't think I pass English. So. Irreflexive. Oh, I'll fix it later. Let me just write down the definition. So R is reflexive if for all A in A is not related to A. In other words, you cannot have any element related to itself. Okay? That's what it means to be irreflexive. So there is no element of the form, or let me say, there is no pair of the form A comma A in R. Okay? None. So you cannot have an element related to itself. All right. So the other notion, so we have reflexive, symmetric. We know reflexive. Now let me say what it means to be antisymmetric. So R is antisymmetric This is kind of related to the symmetric property, but basically what it says is, okay, if A is related to B and B is related to A, then A has to be equal to B. In other words, the only element that you are allowed to have in the relation, so that when you flip them, they are also there, are the diagonal elements. So elements of this form. Okay? So that's what antisymmetric means. So R is antisymmetric if for all A in A and for all B in A related to B and B related to A implies that A must be equal to B. Okay? So in words, so what this means is that if the ordered pair A comma B is in the relation, and if when you flip it is also there, then it must be the case that A is equal to B. So once again, in common terms, what it means is that if you want to have a pair in the relation, so when you flip it is there, it has to be of the form A comma A. Okay? For example, 1, 2, and 2, 1, they cannot be in the relation. If they are, then it's not antisymmetric because 1 is not equal to 2. Okay? All right. And then finally, there is the notion of transitivity. So transitive. So R is transitive if for all A in A, for all B, and for all C. Now, transitivity means, it's like equality. For example, let me say with equality, if A is equal to B and B is equal to C, what can you deduce between A and C? They are equal. That's transitivity property. So if A is related to B and B is related to C, then A is related to C. Okay? So if A is related to B and B is related to C, then A is related to C. Okay? So that's the transitivity property. And let me write it with other pairs. So what we're saying here is that if A comma B is in the relation and B comma C is in the relation, then you need to have A comma C in the relation. Okay? So that's the transitivity property. Okay. Any questions? So now we're going to do some examples, but are there any questions on these definitions? So last time we talked about reflexive and symmetric. Now I'm bringing up these three notions. So irreflexive basically means, remember, reflexive was every element has to be related to itself. Irreflexive means no element can be related to itself. Okay? Antisymmetric means that if A is related to B and B is related to A, then they have to be equal. Okay? Only diagonal elements are allowed to be flipped and stay in the relation. And transitivity, well, what transitivity means, if A is related to B and B is related to C, then A must be related to C. Okay? Just think about it why. All right, so let's do an example. So determine if the relation is any of the above properties. All right, so let's see. First, let's say that A is the integers, and then let's define R to be other pairs of the form A comma B, such that, let's say, A is greater than B. Okay? Let's say this. So we kind of already look at something like this. So for number, let's see the first one. So reflexive, what do you think? Is this reflexive? Yes or no? No. Why? Because 1 is not related to 1, right? Since, for example, 1 is not greater than 1, right? You understand this? So you just need to give me one concrete counter example, okay? All right, so that's reflexive. Let's see, is it irreflexive?
Yes.
let's see. So yes, in this case, this one, yes, is reflexive. Why?
Because you will never have one related to one.
Because, well, you need to show that no integer is related to itself.
Yeah.
So you need to prove it. So how do we prove it? Just one line. It's very easy, but you need to know how to write it down. So how do you argue that there is no integer related to itself? It's very easy, just one line. So proof. Let A be any integer, right? This is any integer. Then, A is not greater than A. That's what you have to say, right? I mean, you just need to really write just one sentence. No matter what integer you pick, it will never be greater than itself, since A is equal to A, in fact, right? But that precisely means that A comma A is not in R. And this happens for any A, so that means there is no element of the form A comma A in the relation. All right, so yes, this one is reflexive. How about symmetric? It's not symmetric. Why? Say that again. What does that have to do with this? So you need to tell me more.
3 is greater than 2, but 2 is not greater than 3.
So 3 is related to 2, but 2 is not related to 3. If you want to use 1 and 2, you need to tell me. It's not symmetric because 2 is related to 1, but 1 is not related to 2. You need to give me the complete picture. You understand this? Okay. So it's not symmetric. For example, we can say because 2 is related to 1, since 2 is bigger than 1, but 1 is certainly not related to 2. You okay with this? All right. So this one is not symmetric. Is it antisymmetric? Okay. That's an interesting background that we have going on. It is antisymmetric. Let's see, what does it mean to be antisymmetric? If A is related to B and B is related to A, then A has to be equal to B. Yes? So is this antisymmetric? So let me write it here. Antisymmetric means that A is related to B and B is related to A, implies A is equal to B. Right? So it means that this will be a true statement. That's what it means to be antisymmetric. So what do you think? Is this a true or a false statement? Why?
Also because it's not reflexive nor symmetric.
To argue that that's a true statement.
Can you argue it's saying that it's reflexive and not symmetric?
Let's say this is not reflexive.
Irreflexive, I mean,
Irreflexive.
and not symmetric.
So why is that enough a justification?
Irreflexive means the same pair.
Remember, you need to argue that this implication is a true statement. And you are not too far off from the So let's see, to prove that this is a true statement, what is it that you need to do?
Prove the conditional statement.
So it's a conditional statement. How do you prove conditional statements? You assume P, try to prove Q, right? And now, what's the problem with P? Can P ever be true? Why?
Since A always has to be greater than B.
Okay, so if you have, for P to be true, these two pieces have to be true, yes? If the first one is true, what happens to the second one? What happens to this? If A is related to B, what can you say about B related to A? It's false. This is telling, if A is related to B, this is saying that A is always bigger than B. So there's no way that then B can be bigger than A. Yes? So one of these two, when one of these guys is true, the other one is false. So it means this part here is automatically false all the time. This will never be true. But if this is automatically false, what happens to the implication? It's automatically true. So this is vigorously true because you cannot prove otherwise. Remember, if you say that this is not antisymmetric, you need to give me a counterexample. How do you exhibit a counterexample? You need to show me an AB and a BA with A different than B inside the relation. But you cannot do that because you won't be able to find those two guys at the same time in the relation. Okay? Remember, if you cannot disprove something, then it must be true. Okay? Because things are either true or false. Okay? This is a statement. The statement is either true or false. If you cannot show that it's false, then it is true. That's what baggage proof means. So, note, if A is related to B for some or for any integers AB, then it follows that A is not related to B. Because A bigger than B implies that B is not bigger than A. Do you understand this? So what this is telling me is that the statement A related to B and B related to A, this is false. Okay? But since this is a false statement, then the above implication is automatically. Do you understand this? In other words, you cannot produce a counterexample. So therefore, R is antisymmetric. Okay, this is very long. Let me see. Is this happening downstairs? No, I didn't see it. All right, so are there any questions as to why this is antisymmetric? This is a little bit strange because the point is we are saying it's antisymmetric because we cannot argue that it's not. That's what's happening here. Okay? We cannot argue that it's not. To argue that it's not antisymmetric, you need to find, an AB and a BA inside the relation for which A is different than B. And we're never going to find that because the moment that a pair is in the relation, when you flip it, it's not going to be there because of the nature of the relation. Okay? If A is bigger than B, then you will never have B greater than A. So you're not going to find B. Okay? So this part here is automatically false, making the implication true. So yes. The reason is because this piece right here is actually false. Okay? Yes.
Let's say any set is not symmetric, would that make it automatically anti-symmetric or not?
No, because let's see. Let's do transitivity, and then I'm going to give you an example of something that's not symmetric and that is not antisymmetric as well. Okay? I'll also give you an example of something that's not reflexive and that is not irreflexive. That way you understand that they are not really opposite of each other. Okay? Yes.
And the proof says then A is not related to B, isn't it? B not related to A.
B not related to A. Yeah. B not related to A. Because if A is bigger than B, then B cannot be greater than A. Okay. So again, I'm also I'll give you an example of something that is both symmetric and anti-symmetric at the same time. Actually, remember last time we defined a diagonal set. The diagonal set is the set that only contains elements of the form A, comma A. That's it. So that one is symmetric because when you flip it, everybody's there. And it's also anti-symmetric because anti-symmetric says the only elements that you can flip are of the form A, comma A. And those are the only ones that you have anyways. So in that case, it's both symmetric and antisymmetric. So you know, they are not opposite. But I give you one that is neither of the two as well. Okay? All right, but good question. And then finally, let's take a look at the last one. So transitivity, what do you think? Is this transitive? Is the relation transitive? Remember the relation. What does transitive mean? Just common sense. The word tells you what it is. So who can tell me out loud what is transitive?
If A is related to B and B is related to C, then A is related to C.
Okay, so what do you think? Does that happen here? Related, what does it mean to be related here?
That A is greater than B.
Okay, so now say it with that word. Instead of saying related, use that word. Say it again. What's transitive?
If A is greater than B and B is greater than C, then A is greater than C.
What do you think? Is that true or false?
I guess it's true.
It's obviously true, right? I mean, the whole point here is to understand what you need to say. Once you understand what you need to say, that's it. Immediately, most of the time, it falls down for you. Okay? If A is bigger than B and B is bigger than C, then of course A is bigger than C because the greater than relation is transitive. This is a transitive relation. Okay? Here we're defining this relation. This is the transitive relation. This is a transitive relation. Okay? Greater than is a relation. All right. So transitive, yes. Let's prove it. Now remember, transitive means, so we want to show A related to B and B related to C implies A related to C. This is what we want to show. So to prove this, what do? We always assume this part and we prove this, right? Assume P, prove Q. So let A, B, C be integers such that A is related to B and B is related to C. Now, this is not assumption. Now, what we want is to argue that then, because of this, A will be related to C. But this is pretty straightforward. So, since A is related to B, then that means that A is bigger than B. And B related to C gives that B is greater than C. So, you have A is bigger than B, and B is greater than C. Therefore, A is greater than C, and this is a property of the greater than, right, relation. So A is related to C. Okay, so if you have that A is related to B and B is related to C, you can always argue that A will be related to C. So that's exactly what it means to be transitive. I'm gonna do something that's slightly more interesting now. All right, any questions? Okay, so to answer your classmate question, let me give you an example of a relation that's neither symmetric nor antisymmetric. Okay, and also let's construct one that's neither reflexive nor irreflexive. So for you to understand that these things are not opposite to each other. Okay, these two guys, 3 and 4, they can coexist together. Now this one, unfortunately, they cannot coexist because this one is saying you either have everybody related to itself, and this one is saying you don't have anybody related to itself. You know, it's two strings. Okay? All right. So let's see, example number 2. So let's make it easy. So let's put A to be a set 1, 2, 3. And R, let's see, R1, I'm gonna make it to be 1, 1, 2, 3. And then let's say 1, 1, 2, 3, 3, 1, and then 3, 2. Okay. With this relation, we are actually going to kill everything with one stone. Let's see. Is this reflexive? So, not reflexive. Everybody understand this? Why? For example?
Doesn't have 2, 2, 3, 3.
We can say because 2, 2 is not in R. Yes? Okay, it's not reflexive. Now, is it irreflexive? Yes or no?
No.
Why? Because 1, 1 is there, right? So this is not irreflexive, and you could say, well, because 1, 1 is there. Remember, reflexive means every element must be related to itself. So you need to have 1, 1, 2, 2, 3, 3. Okay? That's not happening, so it's not reflexive. Irreflexive means nobody can be related to itself. Again, that's not happening here because 1 is related to 1. Yes? All right, now let's keep going. Is this symmetric? Why? Good. It's not symmetric because 3, 1 is here, but 1, 3 is not there, right? It's missing 1, 3. So because 3 is related to 1, but 1 is not related to 3, as far as this relation is concerned. Does that make sense? Now, is this antisymmetric? Why?
Because we have 2 and 3 and 3 and 2, but 2 is not equal to 3.
Good. You see? So, for example, you cannot use this one because this one is fine for antisymmetric, right? You flip it and that equals. You cannot use this one because this one will vacuously satisfy the antisymmetric condition. 3, 1 is there, but there's no 1, 3. So I will make the first part false, making the whole thing work. Now, these two guys are the ones that break everything because 2, 3 is there, 3, 2 is there, but 2 is not 3. You understand this? So, not antisymmetric. And then we can say, well, because 2 is related to 3 and 3 is related to 2, but clearly 2 is not 3. You okay with this? Oh, okay, and now we're here. Is this transitive? Why? So you're right. But why? Yes.
2 is related to 3, and 3 is related to 2, but 2 is not related to 2.
Very good. For example, remember, transitivity basically when it comes to other pairs, it means if you have two guys where the second connects with the first, and they match, the second element matches the first one, then when you can make a new pair with the first and the last, and it has to be there. Okay? So 2, 3, 3, 2, I need to have a 2, 2. If there's no 2, 2, then it's not transitive. For example, you could also use this 2, 3, 3, 1. What do I need to have? A 2, 1. And we don't have a 2, 1 here. So you could use that as a counter example as well. Do you understand this? So when the second guy matches the first one, if you delete those, then you can use the remaining to make a new pair. It has to be there. That's what being transitive means. Okay? You can combine pairs like this. So here you could say, well, 2 is related to 3, 3 is related to 2, but 2 is not related to 2. Or you could say there's no 2, 1. Okay? However you want. So for example, this one right here is none of the properties that I just described. So a relation may not have none of those properties. Okay? It's actually worked out better than I expected. I was shooting only for the others, but it's nice. Okay, so not transitive. Okay, and then the reason is because, for example, 2 is related to 3, and 3 is related to 2, but 2 is not related to 2. Remember, you can either write this or write 2, 3, okay, however you want. Okay, and this is one counterexample. There is another one, 2, 3 with 3, 1, but then there is no 2, 1. Okay, that's another counterexample. Notice that you cannot use these two because yes, you have 3, 1, then you have 1, 1, but that will give you 3, 1. No, we have 3, 1. Okay, so these two you cannot use, for example. All right. Questions? Do you understand this? All right, let's actually do a helpful exercise. Let's see if we can fix it. Let's try to figure out what we can add to this relation to make it, if possible, to make it any of these properties. For example, what do we need to, I mean, the first one is easy, right? What do we need to add to this relation to make it reflexive? So let's just say it out loud. So if we throw in 2, 2, 3, 3, it will be reflexive. Yes? All right. How about irreflexive? Can we add something to make it reflexive? No. We need to take away stuff. But typically, you are not fine with taking away. We like to add things because you don't lose information. You're just adding extra stuff. But the original information is there. You see? So here, there's no way you can make this irreflexive. You have to be able to, you need to be willing to lose information. And typically, we don't want to lose information. Okay? So this cannot be made reflexive unless, of course, that you remove stuff. But typically, that's number one. The question is, can you complete it? Can you add stuff to make it what you want? We can make it reflexive. It's easy. 2, 2, 3, 3. Done. We cannot make it reflexive. Can we make it symmetric? What do we need to add to make it symmetric? So just 1, 3. Everybody okay with this? So because 2, 3, 3, 2, that's fine. We have a 3, 1. We just need a 1, 3, and then we'll be symmetric. Are you okay with this? All right. Can we make it antisymmetric? When I say make it antisymmetric, I mean by adding stuff. Remember, we don't want to be removing things. No, remember, our problem was the 2, 3, and the 3, 2. We cannot just get rid of those, right? So no, we cannot make it antisymmetric. Can we make it transitive? So how? What do we need to add to make it transitive? So we need to throw in a 2, 2. Yes? Let's see. Because I think this is helpful seeing it. So we need to throw in a 2, 2. So I'm gonna put a T here for transitive. We're making it transitive. So we have 1, 1. We have 2, 3. 3, 1. 3, 2. Okay, so looking at this pair tells me that I better throw in a 2, 2. I'm gonna put it in red. Yes? There is something else that pair tells you to throw in. What is it? That same pair. 3, 3. Because if you look at it as 2, 3, 3, 2, that forces to have 2, 2. But you can look at this one first and then this one second, right? If you have 3, 2, 2, 3, then you need to have 3, 3. Does everyone understand what I'm saying? You need to have a 3, 3. Okay, that's what those two pairs give me. Anything else that we should have? So if we look at these two guys, it tells me that you need to have a 2, 1, right? Anything else that we should have? So 2, 1. Do we need a 1, 2? Look at these two. No, we cannot look at this. No 1, 2. So 2, 2, 1. It's 3, 2. That's it. We have a 3, 1. That's it, right? So we don't need a 1, 2 because, for example, here to be able to use this one, we will need to have a 1, 3, but we don't have a 1, 3. If we had a 1, 3, then we would need a 1, 2. And can we make a 1, 3? There's this one here, and then no, that's it. So the point is that to actually decide whether something is transitive when it's given to you as another pair is not that easy because you have to make sure that you find all possible combinations, okay? And sometimes we like to look at it from left to right, but remember, you can swap things and then get new pairs, okay? So understand that you have to find all possible combinations. So I think that here we have explored everything that we can. So that's it. This will be transitive. Okay? All right. Good. Okay, so let me introduce, well, not introduce because you should be familiar with this from doing previous homework problems, but just in case, the modulus relation. So recall, I'm gonna let A be, let's work with positive integers. Actually, let it be an integer. So let A be the integers, then we say that A is congruent to B. I'm gonna use mod 5, but it doesn't have to be mod 5, it can be whatever you want. Mod 5 if a minus b can be written as 5 times some integer equals 5k for some k, for some integer k. So what this means is that these two numbers have the same remainder when divided by 5. So i.e. a and b have the same remainder when divided by 5. Okay? But formally, when you want to work with equation, this is very convenient. So this means that the difference is actually a multiple of 5. Okay? That's what it means to be congruent. And we read this, it's called congruent. So congruent modulus 5. And sometimes you don't write this, but you put the little 5 down here. Okay? All right. So, and this is a relation, so we can define all the pairs of two numbers will be related that if they are congruent mod 5. In other words, if they have the same remainder when divided by 5. So we can define R to be a relation on A, which are the pairs A comma B, such that A is congruent to B mod 5. And by the way, I can do this mod any integer you want. Okay? It doesn't have to be mod 5. All right, so let's analyze this one. Let's go through all the properties. Let's see, reflexive. Is this reflexive? Why? Why is it reflexive? So I'm going to write the property here. For all A, so for every integer, you need to argue that A is related to itself. Remember, this means that they have the same remainder when divided by 5. And it better be, right? I mean, the remainder of A divided by 5 will be the same as the remainder of A divided by 5. Yes? Now, let's do it formally. So, yes, it is reflexive. So, let's say here, yes. So, let A be an integer. Then, I just need to argue that A is related to A, which means that the difference is a multiple of 5. Now, this is very easy. What's A minus A? What is this? 0. And 0 can be written as 5 times 0, for example, right? 0 is equal to 5 times 0. And that satisfies the condition, because remember, this just means that the difference has to be 5 times some integer. I never said what that integer is. It can be any integer, in particular, it could be 0. Okay? And so, A is congruent to A mod 5. Do you understand this? Okay. So A is related to A, and that means it is reflexive. All right. So let's see, if something is reflexive, can it be reflexive? Remember, they are not opposite, but if it is one, can it be the other one? No, because irreflexive means that no element is related to itself, and we just proved that every element is related to itself here. Okay? So it's not irreflexive. So not reflexive. And we say since 1 is congruent to 1 mod 5. Okay? There we go. Okay, number 3. Symmetric. Is this symmetric? Okay, good. So remember, symmetric means for all A, for all B, if A is related to B, then B must be related to A. If you think about it with the remainder point of view, then saying that A and B have the same remainder when divided by 5, it doesn't matter the order, right? Now let's formally say that. So again, to prove this, we need to argue that if A has the same remainder, that if A is congruent to B mod 5, then so is B. Then also B is congruent to A mod 5. Okay, so yes. Remember, let A, B be integers such that A is related to B. So we always need to assume this. Assume B, you want to prove Q. So what does this mean? So it means that A is congruent to B mod 5. And so A minus B is equal to 5k for some k. For some integer k. This is what we know, okay? Now we need to argue that B is related to A. In other words, that B is congruent to A mod 5, which means that we need to argue that B minus A is also a multiple of 5. How can we do that? Just multiply by -1 this equation, right? We have this equation, multiply by -1. So then just multiply by -1 on the left. Remember, multiplication by -1, what it does is it flips a difference, it changes the sign. So then this is going to be equal to -5 times k, which is 5 times -k. But if k is an integer, then what do you know about -k? So then, so we have this, and -k is an integer, since k was an integer. Okay? And this precisely means that B is congruent to A. So B is congruent to A mod 5. And so B is related to A. You okay with this? All right, so it is symmetric. How about antisymmetric? Why not?
Just from a remember point of view, you can have two integers and you have two integers, split them, and they can or cannot be the same.
Give me a counter example. Just tell me something concrete.
5 and 25.
Good. 5 and 25. Right? 5 and 25, they have the same remainder when divided by 5. What is it? What is it? 0. But of course, 5 is not the same as 25. Yes? Remember, just give me something concrete. So antisymmetric? No. Why? Well, 5 is congruent to 25 mod 5. Since 5 minus 25 is -20, which is 5 times -4. Yes? So -4 is an integer, so they are related. And then, of course, 25, of course, is congruent to 5. We just proved that it was symmetric. There's no need to argue this again. But certainly 5 is not 25. You okay with this? All right, so it's not antisymmetric. Transitive. Is this relation transitive? Remember, transitive means that, for all A, for all B, and for all C, if A is related to B and B is related to C, then A must be related to C. Okay? So let's see. So if A and B have the same remainder when divided by 5, and if B and C have the same remainder when divided by 5, what can you say about A and C? They have the same remainder. Okay? Now, the question is, let's make sure that we can write this down formally with the equations. That's why it's always good to know the informal version of some ideas, because it allows you to quickly identify if a certain statement is true or not. Okay? So A has the same remainder as B. B has the same remainder as C. Okay, then A and C have the same remainder. Yes? That's your connecting point. Now let's see how we do that. How do we show that using equations? Okay, remember, how do we prove this? We assume P, prove Q. All right? So let's say yes, it's transitive. So let A, B, C be integers such that A is related to B and B is related to C. Our goal is to show that A is related to C. In other words, A minus C would be a multiple of 5. This is our goal. All right, let's see. If A is related to B, that means that A minus B equals 5k. I'm going to call it K1. for some integer k1. Yes? Now, from the fact that b is related to c, that means that if I do b minus c, that's going to be equal also to 5 times some integer. Let's call it k2. For some integer k2. Now, somehow I want to say something about a and c, about a minus c. So with this information, what can we do to obtain a minus c? I don't have too much time, so let me just tell you. Just add these two equations. What happens if we add up these two equations? What happens to the left side? The b's cancel, and what do we get? So if we add up the two equations, we get a minus c equals, and what do we get on the right hand side? 5k1 plus 5k2. Yes? Now we can factor out 5, and we get k1 plus k2. Now, what do we know about k1 plus k2? Why? Why is it an integer? Because k1 and k2, they're both integers, right? So, and k1 plus k2 is an integer, since k1, k2 are both integers. Okay? And we just showed that a minus c is a multiple of 5, so they are related. So a is related to c. Done. Questions? All right, so notice that this relation, actually this relation is a special relation. By the way, before I say that, did we really did the number 5 really play a significant role in this argument? Did we really do anything with 5? So if instead of 5 I would have written 3, mod 3, or mod 20, mod 2, do you think the arguments here would change? The only thing that would change is that, every place that we put a 5, we put the 2 or the 3, whatever the mod is, right? So the point is that this argument, you can do it verbatim, the same thing, if I write mod n, where n is an integer. Okay, so let me just make this plain, or put this remark. So remark, the above works for any integer n in place of 5. So in place of 5. So if you have a congruent to be mod n, you can play the same game that we did above, and it's gonna work exactly the same way. Okay. Now notice that this relation, this congruent relation, is special. It actually satisfies the 3 properties that I did in red. It's reflexive, it's symmetric, and it's transitive. Relations like this, they have a special name. They are called equivalence relations. Okay? So the relation R above is reflexive, symmetric, and transitive. We call such a relation an equivalence relation. We call such a relation an equivalence relation, and this is the definition. Okay, so what's an equivalence relation? An equivalence relation is a relation that is reflexive, symmetric, and transitive. So when you're given a relation and you are asked to determine whether it is an equivalence relation or not, you need to check 3 things. Is it reflexive? Is it symmetric? Is it transitive? Do you understand this? Now, the reason why we care about equivalence relations is because they are very important, because we can use them to partition sets.